All right, everybody. Welcome to this new developer features in Aerospike session. My name is Mark Nguyen. I'm a senior quality engineer here at Aerospike. I'm here with Joe Martin, our director of engineering here at Aerospike, and we hope to this session give you a quick look at these new features. So Joe, due to some medical issues, won't be able to present today, but as backup, I'll go ahead and begin the presentation. So let's go ahead and move on to the slide. So these are the topics that we're going to be going over. So unlike the other sessions where we kind of go more in depth into a particular topic, we're just going to hopefully be able to take a kind of a quick look at all of these topics and give you guys some exposure to both the topics that you see more in depth in the other sessions, and also for some of the smaller topics where we'll also be able to take a quick look at those. So when we talk about developer features, we're going to be thinking about going over the features that you typically think of as the ones that you use in your applications as you're interfacing with the client libraries. So this doesn't really include, for example, operation type features, such as they just announced new XDR coming with Aerospike 5.0. So, instead we're going to be talking about things like the Bitwise Operations API and the new Hyperlog Log type. So we'll make a small exception at the end to give a look at a couple of other product updates that from our ecosystem that we hope will be interesting to you guys as well. So for the first topic, let's talk about nested complex data type operations. So I think the best way to go about explaining how this new feature works is to go over an example. So Ronan Botzer, our director of product, has a blog on Medium where he new bin value to an existing nested map. So basically, he's able to do this than before. So before server version 4.6, you would have had to do a read, modify, and then write on that record in order to be able to add this new bin value. And due to this, you would end up using more bandwidth, have higher latency, and this can be more problematic, especially as your record sizes get larger. So with the nested CDTs that come with server 4.6, this essentially becomes an atomic operation on the server, which means that we can execute these operations efficiently on the server in isolation under record lock. So let's and on the left-hand side, the key values are strings that could correspond to the players of this game. So that's the key value of this map. The value is a nested list within this map, and the first element of that nested list is the score. So you can see that the ETC user got the lowest score of 9200, and the ACE user got the highest score. The second element of the list is a nested map within this nested list, and you can see that it shows two key pairs in this nested map, one corresponding to a datetime timestamp and one corresponding to a Unix timestamp. So let's look at what we want to happen after we add the bin with an atomic operation. So you can see in the bottom four rows we have the four users, the four players there who have the same data as in the previous slide. But in the first two rows, we can see that we have the an additional nested map added into the the nested map of those datetime maps. So for the ACE user, for example, you can see that within that nested map, with the timestamps, there's now an awards string key and a nested map corresponding to, for example, what might be a high score trophy given to that user. So how can we accomplish this with an atomic operation? So in the middle there towards the bottom, we're defining our operations. So basically, we have, just like before, you would have the operations there passed into the map put API. But the difference there you can see is that at the end, we pass the option there, and we define that at the top. This is basically a map to where we want this nested value to be added. So you can see in this context, we define the map key to be CFO. That is the user that we want to modify. And you can see that the CTS list next is set to the second element of the list, because that's where we want to make the modification with this operation. So in this map put, we end up putting the scores bin with this awards, and they can also see the, you can also see that we added that previous slide. So we could also have put another operation in here to update the other user, as you saw in the previous slide. In this case, I'm just showing this one for example, for simplicity. So with Server 4.9, one additional feature that was added to this feature was that you can actually create a nested CDT with an atomic operation, even if it didn't exist yet, as it did in the previous example. So that's another thing you can take advantage of if you upgrade to Server 4.9. So this was just a quick look at this. If you want to see more detail and more information, I recommend looking at Ronan's blog on Medium called Operations on Nested Data Types in Aerospike. You can see both an explanation of all the different ways he's using this new feature, and there's also a link to the GitHub repo, which you can download and then run this example for yourself. And of course, our client API documentation is something you can use depending on which client library you'd like to use. So moving on to the next feature, let's talk about the Bitwise Operations. So again, I think this will be easiest to go over if we just go over an example use case. And again, I'm going to use one of Ronan's examples. And in this case, what he's trying to do is to set a single bit for a byte data type record. So for 4.6, again, you would have had to read record, modify, write it back, and with all the overhead that incurs. With 4.6, again, this will be an atomic operation on the server instead. Example, so variable, he's setting a single byte with the maximum value, all the bits set to 1, by using the maximum 255 value, and setting it with the size of 1. So we're going to use this later at the bottom of this client operate call. So way at the bottom, you see we have a Bitwise Operations .bitset API call, and that buff object at the end is passed as the last parameter. So on the right-hand side, we have a list of what the Bitset API does. So you can see that last value corresponding to the buff variable corresponds to the value to be set. Just before that, we set a value of 1, and this corresponds to the value byte size, the size of the value in bytes, which we initialized to 1 when we set this buff variable. The bit size, we set this to 1 as well. This refers to how many bits of the value to write. And in this case, since we want to set one specific bit, we're also setting this value to 1. And just before that, you can see we have the 1421 value. This is the offset that we want to set for minute 1421. So one Bitwise Operation API to use, the Bitset API, which here you can see for the write APIs. We have other ones such as resize, insert, and remove. And for the read APIs, we have ones like get and count. In Ronan's example, he also uses the get API, the Bitget API, in order to verify that the set went through correctly. So if you look at his examples there, I have a link here to where you can find it. It's in Aerospike examples, Aerospike modeling, and the Bitwise Operations script. You can see how he ran this previous snippet and many more, including the verifications. If Python's not your thing, we also have another blog written by one of our solution architects, Reuven Caslin. He did an example using Bitwise Ops in Java, using our Java client library. So you can also take a look at that. For reference, of course, our client API docs has all the information you need to use the API for your respective client library. And there's more information on our Aerospike documentation, especially explaining more about these read and write APIs. So you can just search for that and find our Aerospike documentation on that. So with Server 4.7, we introduced some operation optimizations. The first one we're going to talk about is the delete operation. So the delete as an operation essentially allows for you to be able to do an atomic read and then delete in your multi-hop transactions. So previously this with workarounds such as using UDF, which would have resulted in much lower performance. Or if you knew all the values of your bins, you could try setting all those bin values to null. So instead of doing that, you can now do this as an operation. So an example use case given was that you could, for example, have a single-use password value. And perhaps in this case, you would not want there to be any gap between reading the password and deleting it. So in this case, you would want to be able to do this multi-operation transaction where you would read it and then delete it. So we have basically a Java client example here just to show how easy this is. So you can just see that as you could call in the Java API, your client operate as usual, and then when you pass your operation list, you could pass an operation.delete in order to take advantage of this feature. So looking at the second optimization that came with Server 4.7, we added predicate filters. So these predicate filters are basically conditionals that you can use for your read and write operations. So one thing that this can be helpful for is both when you're using read and writes and you're using the Java client library, is you could avoid having any exception handling in your application by just having these predicate filters defined as your conditionals. So you could, for example, check for existence rather than trying to catch these exceptions. So other example use cases for write operations are you could write if a value didn't exist in your bin, or you could, for example, use cases for read operation if filter and you want to check for a region before doing your read op, or you could you might want to treat a record as conditionally non-existent, for example, with using as if it were a TTL value. The third example use case is you might want to combine with batch read for having a scan query type behavior when using these predicate filters. So let's go ahead and look at an example. This is actually a snippet pulled from the Java client library tests. So it doesn't include all of the initialization. Just want to show how the main flow of the logic works in terms of using these predicate filters. So you can see in the middle here, we define a write policy where it says predx equal 1 w policy equals new write policy. So in this policy definition, you can see we're calling a new API called set predexp, and this set predexp is something that we are saying we are setting such that the integer bin value, the integer bin, which corresponds to the bin A name value, must equal 1. And this is the condition we're essentially seeing for our predicate filter. So, so how do we test this in this test? At the very beginning, in the first 4 lines, you can see that we're initializing the bin values and putting these bin values into the respective keys. For key value 1 and bin A1, you can see that the bin value is set to 1. And for key B and bin A2, you can see that the bin value is being set to 2. So when we go to the bottom here and we see we actually run the test to put an updated value to this record, to these key A and key B records, we and use the policy we defined above with the predicate filter, you can see that the first put actually succeeds, and that's because it was initialized, and therefore it passes the condition for this predicate filter. And then you can see for the second one where we had key B, which was using the bin value set to 2. The condition does not pass the condition we set in the right policy that we passed there. So key B will not end up being updated because the bin value is set to 2 and the assertion shows what we expect. So moving on, we have another type of, we have new scan options. This one, background scan operate, I believe is released with 4.7 as well. So this is this is a new feature where you can use a background scan operate as an alternative to background UDF queries. So again, similar to before, this removes any dependency on UDFs, so you can get much better performance, especially with your larger record sizes. And due to not needing to use the UDFs, it also removes any dependency on Lua. So if, for example, you're using the Java client library, you wouldn't need to know the Java client language, and you wouldn't need to know Lua as well in order to define your background UDF. You can instead just use the background scan operate API within the Java client library. So this feature supports write operations, and it ends up, based on what's found, it'll end up being applied to all the found records of the scan. So it also supports multi-operations transactions, including operations from our list and map APIs, the Bitwise APIs that we discussed previously, and the Hyperlog Log APIs that we'll discuss soon. So one example use case for using this feature might be, let's say you had a record where the record bin value corresponded to a map with an ID key, and it had a TTL as part of a nested list. You could, for example, just use a background scan operate to trim all the key value pairs where that TTL value is older than a specific value. So let's go ahead on the next slide and take a look at an example of this. So again, this example is pulled from our Java client library tests. So the first thing we do in this example snippet is we will initialize a statement for a query as usual. So you'll probably recognize this from using the query APIs from before. So in this case, we're setting the namespace, the set, and a filter range for this statement for this query. We're also going to initialize a bin value, which we're going to use next when we actually call the new API. So in the middle there, you can see when we call client.execute, this is us calling the this is similar to API we might have used before if doing a background UDF. But in this case, instead of passing the UDF information in order to invoke it, we're going to pass an operation put of that bin value we initialized. So that's how we can basically invoke this new feature. So since this is an asynchronous call, which the command is actually completed, we can take advantage of the fact that this API returns a task, execute task object, and one of the APIs in this task object allows us to block so that we can test that the command succeeded successfully before moving on to the next test. So in this case, we're just calling the wait till complete API to wait 5 seconds with a total of 2 seconds, such that we'll be able to block on that, and then we can do a normal query and iterate through those query results and verify that the write op succeeded from the previous step. So moving on to the next scan option with server Aerospike Server 4.9, we added a new feature called Scan by Partition. So previously, all of the scans were serial by namespace. With this new Scan by Partition, we can essentially have our scans run in parallel across all 4,096 partitions of your Aerospike cluster. So an example use case of this is Aerospike Connect for Spark. We've observed that in some of our initial use cases, we've had very large performance improvement due to being able to take advantage of this newfound parallelization when using Spark. So that was one example where we have already seen a lot of great benefits from taking advantage of this new feature. So some possible use cases for this. One is you may want to do a correct scan. So that will, when you're using scan by partition, this will work properly even during cluster disruptions and migrations. So scanning by partition will result in proper results regardless of those conditions. As previously mentioned, you can use Aerospike Connect for Spark and take advantage of this feature by configuring your Spark to have control over how you want to parallelize across your partitions. And another use case for this is if you wanted to paginate over a single partition, and you can do this by specifying, for example, in the Java client API, a max records value. So this will end up controlling the size of your page. This is something that in the Java client you would set in your scan policy. You can also set the after value. This is something that you will use to specify the key digest that you want to start after. So when you get one page result and that ends up being returned to you for your first page of your partition, you can take a look at what the last digest you received in that page and specify this as the after option to the next request you make when you do your scan by partition. So that will end up resulting in having the next page starting with the correct value based on that digest that you sent in the after option. So you can imagine that this is also corresponding to like a max records corresponding to like a count kind of value, and the after value corresponding to like an offset for your page. So the final scan option that we want to talk about is scan by max records. So in this context, we're actually talking about scanning records in a regular scan, which samples evenly across all of your partitions rather than specifying a specific partition or a partition range. So in this case, when you specify maximum number of records, this is in place of what you would have previously set as an option, and that would have been giving the percentage value. So that percentage value is now deprecated. And so we hope that starting with server 4.9, our users will scan and specify the which should never return more than the max records value that you set, though it may end up returning something slightly fewer. So again, let's look at a Java client example where, or at least let's look at the options you would set. So in this case, for the Java client, it would be as simple as when you define your scan scan percent value would be. So let's go ahead and look at Hyperlog Log. This is another feature which was released with our server 4.9 server. The Hyperlog Log bin data type is able to give us estimated counts of distinct members of a large data set. So typically when we want to use Hyperlog Log, it's because we want to sacrifice some accuracy. And in exchange, we use up less computing and storage resources. So, and the way we do that is by taking advantage of this algorithm. And the gist of the algorithm is that the general algorithm itself is that we want to hash each element of the data set. Based on this hash, we want to find the longest sequence of leading 0 bits in order to estimate the count of distinct members. The this estimate ends up working because, as you might imagine, if you have a lot of distinct members, this hash function will end up hashing your elements into a lot of distinct values. And the more of these distinct members you have, the more likely you'll end up with a particular type of value, which would have a long sequence of leading 0 bits. So if you have a lot of distinct members, you end up with a larger value for this value. And if you have not many, then it's much less likely due to the probability of it that you would end up with a very long sequence at all. So based on that, we get a pretty good estimate of what the distinct member count is. So another thing that the algorithm does in order to reduce the variance is to bucket these estimates into various subsets, and then averaging them out in order to basically reduce that variance that can occur from this. So basically, let's talk a little bit more about what this data type can return. First, I want to define something called similarity. What this refers to is a ratio of the distinct elements in your intersection to your distinct elements of the union of your sets. So, for example, in the best case highest similarity score, you could end up with a similarity score of 1 because the elements would be the same, and so the values at the top and bottom of this ratio would end up being the same. The worst case would be 0 for a completely disjoint sets because the top value of this ratio would end up being none. Of course, it'll be more likely in your real-life data sets that you would get some number in between. So just depending on what this ratio ends up returning, you'll end up with either a higher similarity score or a lower similarity score based on those. So the Hyperlog Log data type can return the following. It can return the estimated size of a set. It can return the estimated distinct element count of the union of multiple sets. It can also return the estimated union of multiple sets, which this return value would end up being its own Hyperlog Log data type. If you specify min hash bits as an option in the API, you end up having this result in using something called a hyper min hash. And you'll typically want to set this when you want to find the estimated similarity, as we discussed above, of multiple sets, or if you want to find a distinct element count of the intersection of multiple sets. So some sample use cases of where Hyperlog Log might be useful, if, for example, it could be if you were doing bank fraud and you wanted to estimate the count of a number of suspicious indicators for each account. Another example might be if you were doing an ad campaign and you wanted to find the scope of it by estimating how many viewers you have per target user group that you have in your data. And another example might be if you have some kind of online sales and you want to test what your conversion rate is into purchases. So you might want to estimate the count of those purchases based on the user group data you have, user item interest, or based on the number of sessions that your customers are bringing up. So to find out more, these actual sample use cases are actually covered in a bit more detail, along with more information about the Hyperlog Log website, and data in our Aerospike website should show up. And we also have a blog from Paul Jensen, in which he goes over all the 4.9 features, including more about the Hyperlog Log algorithm and how that works. Of course, if you want to actually try this out, you can take a look at our client APIs and see how you could take advantage of the Hyperlog Log data type. So another feature that we have is transport compression. I believe this was released with our server 4.8 server. This is something when set is able to compress both the client request and the server response. So this is something which is not the same as storage compression, which we had released previously. This is instead compressing the network traffic, the client request and server response. So in this case, the application has actually complete control over which transactions are compressed, unlike storage compression where you would configure that on the server. So this compression is also independent of the storage compression, so it doesn't have any effect one way or the other if you're using one or versus the other. One reason you might want to use this is if you want to increase your throughput potential. So this is something that where you could sacrifice your CPU and memory usage in order to have better throughput results. So you end up using a bit more memory for the extra compressed buffers, and of course you'd end up having more CPU. But this could be for example, in cloud deployments, if let's say you have limits on the amount of network traffic that you can deployment, or if you just want to reduce costs due to the network bandwidth used, and you're willing to sacrifice CPU overhead in order to achieve that. So again, as an example, if you wanted to try this out in the Java client, you could do this as simply by setting the compress option when you initiate your client policy in order to enable transport compression. So let's also talk about a couple of other product updates within our ecosystem. First, let's talk quickly about Aerospike Connect for Kafka 2.0. So the outbound connector includes now more serialization formats, including Avro types. So that's something that should prove useful. We also now support configuring Aerospike record bin mapping, and we support being able to specify this bin mapping and other routing and format configurations at the set and namespace level. For the inbound connector, we pretty much had a rewrite of this inbound connector, which now provides guarantees on Kafka record consumption. It also adds TLS and delete operation support and more flexible options. For example, with your Kafka keys, there's more ways you can configure that as part of your inbound connector usage. It also added support for retry on write errors. So another product update, we released Aerospike Connect for Spark 2.0 as well. As we previously mentioned when we talked about the scan by partition feature, this now allows you to fine-tune up to 4,096 scan partitions concurrently. You can also configure TLS and LDAP now, and you can now query multiple primary keys through the connector itself. With the 2.1 release, we now also have support for streaming writes. So you can take a look out for that and then hopefully give that a try. We also announced and have a few products in beta for our Aerospike Cloud. So we now support Kubernetes deployments with Helm charts. So you can use the Helm chart package manager to do a quick and easy deployment of Aerospike into a Kubernetes deployment. And you can also use the Kubernetes operator. So this is obviously optimized for managing, configuring, and deploying your Aerospike clusters, specifically optimized for Google Kubernetes Engine and Google Cloud Platform. So we have that in beta, and we hope you can give that a try. And we also are introducing an Aerospike monitoring stack. In this case, we take advantage of Prometheus for alerts and monitoring, and we also integrate with Grafana for visualization tools. So obviously, we went over these quick in some of the other sessions, and more in-depth looks. For example, I think tomorrow we have a session on Hyperlog Log, which I hope some of you will be able to attend if you want to find out more about how that works. We also had some sessions on, I think, taking advantage of the nested CDT ops, and the cloud, Aerospike cloud products like the Kubernetes operator. So I think those will be available for download soon. So you can find out more details about that if those topics were interesting to you. So let's see, I think we can go to questions next. So one question I think is that some people have asked if the client libraries are supported across all of our clients. For example, the latest features, can you use like the Python client to use the Hyperlog Log API? We typically, when we release a new feature and it just comes out with the server, we typically have support for our C client, our Java client, and our C# client. The other clients will typically add support soon afterwards. So with the other clients, hopefully you would be able to use those pretty soon if those are the clients you hope to use. So I'm looking here to see if we have any other questions. Okay, doesn't look like we have any other questions. So I think we're also coming up to close to the end of the session. So if you do have any more questions, we have a Slack channel for the summit, which you can ask questions there. We'll have all of our experts on standby, which can probably provide in more detail for any of these features. And we also, I think, have a developer hub, which you could try out to see if we can find some help there. Otherwise, I think that's it. So thank you very much for attending this session, and I hope you all have a nice day.